Thanks, Jonathan. So yeah, thanks for all the organizers for putting on this nice session. It's been really nice. So yeah, I want to talk about this probably my favorite non-existence result in mathematics, which is non-existence of projective plane of order 10. So who's actually heard of this result? Okay. So yeah, there's a lot of people up on projective geometry in this session, but I'm going to start at the beginning. It's a pretty famous result. So what is a projective plane? So we all know Euclidean geometry, right? Where Euclid defined his axioms 2,000 years ago. You have points, you have lines. Any 2 points, there's going to be one line through those points, right? Exactly one. Now, if you have 2 lines, they may or may not meet at a point. They might meet at one point. They might be parallel. They don't meet at any points. In projective geometry, we're actually going to have a different axiom, which says any 2 lines meet at a unique point. Okay, and actually this, first it's counterintuitive, but it actually makes sense. So if you think about the artists who first started painting scenes in 3 dimensions onto a canvas, they realized that parallel lines in 3 dimensions would actually meet on the horizon, or at least they seem to meet. So what you can do is actually add a new line into your plane, this line at infinity, and then the formerly parallel lines, like these black lines on the screen, they're actually now going to meet at this new line at infinity. And so what we've constructed here is called a projective plane, right, where any 2 lines are going to meet. And so we can axiomatize this. There's 2 simple axioms. Every pair of lines meet at a unique point, and every pair of points define a unique line. Okay, so those are going to be my 2 axioms. And in a similar way, where once you know about the real field or the rational field, these are infinite fields, you can ask the question, well, is there a model of the axioms of a field which is finite, right? And it turns out there are, right? Finite fields, we've heard a lot about them. Well, let's ask the same question. Do finite projective planes exist? Right? Is there a finite set of points and lines which satisfy those 2 axioms? Well, it turns out it doesn't take very long to find one. This is a pretty trivial example. It's just a triangle. But it really demonstrates the principle, right? If you have the lines be the sides of the triangle and the points be the vertices of the triangle, then yeah, indeed, any 2 sides are going to meet at one vertex, and any 2 vertices are going to define one side. Okay, so that's a very simple case. These are more interesting ones. Here's the next easiest example. This is a famous plane called the Fano plane. So there's 7 points represented by the dots, and then there's 7 lines represented by the 6 lines plus a circle. Right? So you might look, it's a bit strange. Why do I represent it as a circle? Well, I can represent it however I like. Right? As long as these lines satisfy the axiom, which they do, right? You can check if you consider that circle a line, take any 2 lines, they're going to meet at one point. Right? So this Fano plane, we drew it in a weird way, but it does satisfy axioms of projective plane. And in fact, you can go even higher. I'm going to stop drawing them at this point because then it becomes too hard to figure out all the colors. But there's 13 colors here, 13 lines, 13 points. Any 2 lines meet at a unique point. Okay, so once you start studying these things, you realize pretty quickly that if they do exist, every line's going to pass through the same number of points. It's kind of an invariant of the plane. It's called the order. Well, actually, the order is going to be 1 less than the number of points on every line. So an order n projective plane was going to have exactly every line go through n plus 1 points. And we can count how many total lines are going to be in a order n projective plane. It's going to be n squared plus n plus 1 points, same number of lines. Okay, so this is all pretty classical. And what we're going to do is going to be pretty crucial, is to represent projective planes in a way which is easy to, because the diagrams get too cumbersome past about order 3, through incidence matrix. Right, it's a 0-1 matrix, which just captures the set of what points lie in which lines. Right, so you have to fix an ordering of the points, fix an ordering of the lines, and then you're going to have a square matrix where the ijth entry has a 1 when line I goes through point j. Right, so it's a pretty easy construction to go from the triangle to the 3x3 matrix there. Now the very bottom, the last sentence, right? This is the axiom that we have to satisfy. Any 2 rows of this matrix have to have an inner product of exactly 1. Think about it, right? If it had an inner product of 0, essentially they're saying that you have 2 parallel lines, right? They don't intersect at all. Whereas if they had an inner product of 2, well, then you're saying you have 2 lines which would intersect twice at 2 points. Well, that also can't happen, right? Projective planes are very restrictive. Every 2 lines have to intersect exactly once. So any 2 rows of this matrix have to have an inner product of exactly 1. And you can convince yourself with the larger ones here, right? So this is a Fano plane, 7 by 7 matrix. Again, any two rows of an inner product of 1. And here's the order 3 case, 13 by 13. Same thing. Okay, so you might already have the question, famous problem. What orders do projective planes exist in? Well, it turns out, you can have a finite field construction. They exist in all prime power orders. And in fact, there's a very famous conjecture, the prime power conjecture, that they only exist in these orders. So you can't find a projective plane of a non-prime power order. This is kind of a risky conjecture, I think. I don't know if anyone actually has even a heuristic argument why this should hold. Right? It's just, the argument is no one's found one. That's pretty risky in mathematics, right? No one's found a projective plane in a non-prime power order, so the conjecture is they don't exist. But I don't know if anyone has a good reason otherwise. We do have non-existence in some orders. So there's this famous Bruck-Reiser theorem. So the conditions at the bottom, if n is 1 or 2 mod 4, and n is not the sum of 2 integer squares, then n is not the order of a projective plane. So 6 fits this bill, right? 6 is 2 mod 4. 6 is not the sum of 2 integer squares. So this is what we have up to 10, right? Bruck-Reiser rules out order 6. Every other integer up to 10 is a prime power. And 10 obviously is not a prime power, but 10 is the sum of 2 squares. So Bruck-Reiser doesn't apply, right? Obviously, if the prime power conjecture is true, then there's no projective plane of order 10. But we can't rule it out by Bruck-Reiser. So this was a famous problem, right? For decades, people wanted to answer the question, right? This is the first open case. And this is called Lamb's problem now, right? Does the projective plane of order 10 exist? So if it did exist, it's going to be pretty large, 111 lines, 111 points. Every line passes through exactly 11 points. If you look at the incidence matrix of this thing, A, it's going to have a very nice structure if you multiply it by its transpose. You essentially get a matrix of ones except for the diagonal, right? And the ones come from the fact that any two rows of an inner product of 1, right? Because A times A's transpose is essentially taking all pairwise inner products of the rows. So basically, A times A transpose would be very structured, but no one knows if A exists. So this is a problem is named after Clement Lamb, who was a Canadian mathematician. He did his PhD at Caltech under H.G. Reiser of the Bruck-Reiser theorem. And an interesting story, right? He goes to his advisor looking for a thesis topic, and he proposes, I want to work on the projective plane of order 10, right? Does it exist or not? And they both, Reiser was very interested in this topic as well, but he says, I think this problem is too difficult. I don't think you should work on it. So what do you think Lamb did? The problem that's now named after him. Well, he chose a different topic, right? And this is for the students in the audience, this is probably a good moral, right? You probably listen to your advisor in matters of this form, right? So he chose a different topic. This problem was too difficult, or he didn't want to risk it. So he got his PhD. He became a professor at Concordia in Montreal. And then he got tenure and then started working on this problem. And what became a 10-year-long saga. So he worked on this problem for 10 years. So this is the next half of the talk, is how did they solve it, right? So it's a beautiful, just a beautiful proof. It relies on essentially coding theory. In fact, just a linear code. So it's the simplest type of coding. Essentially, we're just doing linear algebra over a finite field, and the simplest finite field, F2. Right, so we're just going to do everything mod 2. If you take a matrix and then the row space of that matrix mod 2, right? So the sum of all the rows form what's called a code, right? This code, we'll call it C. It's going to be a subspace of F2n. And here's the cool part, right? You can prove things about the code associated with a projective plane, right? Its incidence matrix. Here's the first theorem, right, from Asmus and Madsen, 1970. So A is the incidence matrix of a projective plane of order 2 mod 4. Then the code has exactly dimension. It's going to be half the rows of A rounded up. So, Fano plane is order 2. So it satisfies this. And Fano plane has 7 rows in its incidence matrix. So by this theorem, the dimension of the Fano plane's code is going to be 7 divided by 2 rounded up is 4. And so because it's so small, I can actually just give you the code. All right, it's going to be 2 to the power of the dimension vectors in this subspace, right? And because it's 2 to the 4 is 16, I can just list them all out for you. Okay, so here they are. The ones on the left, we have the 0 vector, which is in any subspace. Then you have the vectors of the incidence matrix of the Fano plane. And then on the right, I have all the linear combinations of the vectors on the left. Turns out, so there's 16 of them. And so what we're going to do now is we're going to count these vectors very carefully. We're going to count them by what's called the weight, which is just the number of ones in every vector, right? So what we have is a weight 0 vector. Then we have a weight 3 vectors. In fact, we have 7 weight 3 vectors on the left. And then we have a weight 4 vector, 7 weight 4 vectors on the right, and then 1 vector weight 7. So this is called the weight distribution, right? We're just going to count all the vectors by weight. In fact, we're going to put this into a generating function, this weight enumerator polynomial, just a way to concisely capture the weight distribution, right? So the polynomial here, the coefficient of x to the I is just wi. That's the number of vectors of weight I in this code. So the code I just showed you, the weight enumerator polynomial is going to be 1 plus 7x cubed plus 7x to the 4th plus x to the 7th, right? Because we have 1 vector of weight 0, 1 vector of weight 7, and 7 vectors of weights 3 and 4. Okay, so we can work it out. Now, because of the session, right, it's all about counting. This is the part of the proof where we're going to do some very careful counting. And it's a bit weird because, remember, we don't know if this code exists, right? In fact, it turns out it doesn't. But what you can do is you can count the vectors of this code by weight, assuming it exists, right? We already know from that theorem I showed you that the dimension of this code, if the projective plane of order 10 exists, the dimension of the code is exactly 56, right? Because it's 111 divided by 2 rounded up. So if that code exists, it's dimension 56. Then we're going to count, or Asmus and Matson count, the vectors by weight, and they can get pretty far. Okay, there's always going to be 1 vector of weight 0, the 0 vector. That one's obvious. The other ones are not so obvious, but they count them. There's no vectors of weights up to 10, from 1 to 10. There's exactly 111 vectors of weight 11. And then there's no vectors of any weight which is 1 or 2 mod 4. So pretty restrictive, right? And then there's also a symmetry condition, right? Essentially, it's saying the count of the vectors of large weight is going to be equal to the count of a vector of a small weight. Largest possible weight is 111. Smallest possible weight is 0. And you actually have a symmetry, right? Where there's the vectors of weight 111, or the count of those is equal to the vectors of weight 0. So putting all these facts together, you get the entire weight distribution up to just 22 unknowns, which I've listed here, right? Or at least the small ones. So the first one is W12, and then there's others too, right? So we have 22 unknowns. So we got pretty far with just by counting using some counting arguments. And then we have this really magical theorem called the McWilliams identity. So it's based on this, what's called the dual code. Now, this is just, if you know linear algebra, right, it's orthogonal complement, right? So in 3 dimensions, you have a plane. What's the orthogonal complement? Set of vectors perpendicular to the plane, right? So the orthogonal complement is pretty, well-known notion, but you can do the same thing over a vector space over a finite field. Things are a bit weirder because you can have self-orthogonal vectors in finite vector space, which doesn't happen, besides the 0 vector, doesn't happen in Euclidean space. However, here's the really magical theorem, and this theorem is like, it's like a magic trick to me. Like you watch a magician do a trick, and if you don't know the secret, you're just kind of amazed. So this is the theorem to me, right? Like, where does this come from? You can convince yourself it at least is plausible. Like, this thing on the right is going to be a polynomial when you do the cancellation. So I've written it with the division. But when you do the cancellation, it will be a polynomial. But why is it equal to the... So when Williams' identity gives you the weight distribution of the dual code in terms of the weight distribution of the original code. Why should this be the case? You have to ask Jessie McWilliams, who proved this in her PhD thesis in 1961. So this is a powerful theorem of coding theory. And what we're going to do is actually, what you can do is work out both sides of this exactly in terms of the 22 unknowns. You're going to look at the left side in terms of the 22 unknowns and the right side in terms of the 22 unknowns. And then you can expand out the right side and you can equate the coefficients because we know they're equal. And when you do that, you equate the coefficients. This is where, and remember Doug Stinson's talk from yesterday, right? He had that comic, the two mathematicians at the chalkboard, a bunch of equations right in the middle. This is where a miracle occurs. Well, this is where the miracle occurs. You do that, you equate the coefficients, and you actually go from 22 unknowns down to just 3. So it's amazing, right? Every coefficient in this weighted numerator is totally determined in terms of the first 3, W12, W15, and W16. For example, right, the coefficient of x to the 19, which is the number of vectors of weight 19, is exactly this expression right here. So this is a very careful count of the vectors of weight 19, right, in terms of the vectors of weights 12, 15, and 16. So why these coefficients on this expression, I have no idea, right? It comes out of the McWilliams identity. So you get this amazing identity now that we're going to use to continue on with the proof. Essentially, it's a very restrictive condition on the number of vectors of small weight, right? So at this point, things take a bit of a turn. So I haven't mentioned yet, but this is actually one of the first big computer-assisted proofs, which is kind of my research area. I'm actually a computer scientist. And so, but along with like the four-color theorem, this is one of the first big computer-assisted proofs. So how does it go? Well, we're going to make the assumption, or what Lamb does is he makes the assumption, okay, let's look at the first unknown coefficient in the weighted numerator, is W12. Let's assume it's positive. So there is a vector of weight 12 in the code. That's a pretty strong condition. And based off this condition, what does he do? He generates what I call a nightmare Sudoku. This thing. I haven't even shown you the whole thing. It's 111 rows and 111 columns. And it's a little bit, so everyone knows Sudoku, right? It's the 9x9 grid. You have to fill in every entry 0 to 9, no duplicates in any row or column, and there's other rules. This one is different. It's a binary Sudoku. So every entry in this enormous matrix is either 0 or 1. And I've given you some of the entries are fixed, just like in a normal Sudoku. Now, the thing which is different from a Sudoku is the rule that you have to use to fill in this matrix. The rule is, going back to the beginning, any two rows of this matrix have an inner product of exactly 1. Right? If you could do that, then you're completing the instance matrix of a projective plane. So imagine like going to your newspaper and instead of your Sudoku, you have this puzzle. Well, you couldn't do that because no one reads newspapers anymore. But in theory, you could do it. Yeah, you could say, okay, there's a 1 in there here that implies there's a 0 here that implies there's a 1 here, and so on. You work out like a normal Sudoku. Oh, you better bring a pencil, right? Because you're gonna have to erase and go back. It's a very, very hard problem, and in fact, it's very hard indeed because there's actually no solution, right? If you really hate someone, you can give them a Sudoku, doesn't have a solution. So this is what obviously it was a computer. This is where it's computer assisted. That enormous Sudoku which was generated, turns out it has no solution, and this was done by state-of-the-art computing in 1980s. So this is a photo of the computer that was actually used to show this. And by the way, the computer's not in the foreground. The computer's in the background, right? It's actually this beige cabinet, this big thing. That's not a cabinet, that's the computer. Right, so you have got some terminal to interface with it, and then you got some tape drive over here to write your results to actual tape. Anyone use this computer before? It's before our time, right? The computer come a long way since this thing. As this VAX machine, right? So it took 183 days, and a VAX runs on about 1 million operations per second. And at the end of the day, because that Sudoku had no solution, essentially what this is, if you trust the computer, it's a proof that there's no code words of weight 12. Because if there were, Sudoku would have had to have a solution. And so then that solves essentially one case. You kind of do the same thing. You generate other Sudokus for weights 15, 16, 19. And some of them are more difficult. Some of them are easier, some of them are difficult. The most difficult one is the weight 19 case. And I've scaled these times so that they would, if they ran on that VAX machine, this is about how long it would take. It would take about 35 years to solve the weight 19 Sudoku. And they didn't do it on that VAX for this one. They did it on a supercomputer which took about 3 years, and it wasn't even running full time. So it was still an enormous amount of computing, though. And in fact, what happened was they got a lot of press. So they got into the New York Times. This is from Science magazine, right? The headline, because it was a problem. It dates back 200 years. It was solved by massive computer search, so it had a lot going for it. And it was really just, the math was really cool, right? They showed essentially an inconsistent weighted numerator, because they showed all the Sudokus had no solutions, which implies the non-existence of these code words, which, and then it violates that count on the number of vectors of weight 19, right? Like, these all can't be 0 because that violates the count. So the counting was totally crucial to this whole enterprise. Okay, the last thing I want to mention, if you're anything, some of you might have a little nagging feeling in the pit of your stomach, and myself included, because everyone's used to computer, and everyone knows they don't always give you the right answers, right? So this is particularly problematic for a non-existence proof. Because what if there's a bug, which almost there always is, and what if the bug causes the plane to be missed, right? There actually was a solution, but the programmer, had an oversight and missed the solution. It's normally not the hardware's fault. Normally it's the programmer, right? You just can't, there's so many edge cases to consider. It's very, very difficult just in practice to write bug-free code, almost impossible, even for simple programs, unless you actually use formal verification of if you can prove the program's correct. It's likely to have a bug. In fact, we actually know now that they did have a bug, because one thing I did about 5 years ago, I was working with Brett Stevens and Kevin Chung at Carleton, and I was doing a postdoc. And what we did was we duplicated their search, but we did it in a way that's less error-prone. We didn't reduce to a Sudoku, we reduced to a logic puzzle, right? So what's the advantage here? You generate this enormous logic puzzle, but the thing is, there's these what are called SAT solvers, and SAT solvers are actually designed to solve logic puzzles, which are very large. And so what happens is then you have a logic puzzle with no solution. And the thing is, it's much less error-prone because the SAT solver already has been written, it's already been optimized, it's already been tested. So I didn't have to write the search code. I just had to generate the logic puzzle. And what I actually found when we compared with Land's original search was a few inconsistencies. Also with Brett had a master's student who also did an independent verification. So it's a bit, we found inconsistencies with that result too. So it's a bit embarrassing because there's 3 publications in the literature. They're all inconsistent with each other. But we're hoping that ours is right. And I'll give you one reason why we think ours has the correct count. Essentially, there's another reason to use the SAT solver, which is the SAT solver actually provides you with a proof of non-existence. So if the SAT solver says this logic puzzle has no solution, it actually will provide you with a proof which can be certified by a proof checker. So that is a much higher degree of rigor, right? Because the proof checker is actually much easier to write. In fact, some proof checkers even have formal proofs of correctness, right? So you can pretty much be very confident in the proof checker. So that part I'm not worried about. There's one nagging little possibility of doubt here, which is the generation of the logic puzzle. That used code which is untrusted, right? So once you generate the logic puzzle, we're pretty confident that has no solution, right? Because it's verified with the proof checker. But the code which generates the logic puzzle, that's untrusted. Now the code, granted, is much easier. It's much easier than a search algorithm. So but there is still some trust there, right? So what we're hoping to do, put together a team, is to actually verify the entire thing in a theorem prover, where then there's very little source of doubt, right? Because the theorem provers are well-tested pieces of software, and so that's how you put the non-existence results like this on a very sound foundation. So, thank you.